Right, so the Programmable Flasher, this started off life as a very simple project that I thought I'd knock up in an afternoon. But as usually happens with simple projects, it wasn't quite as simple as that. So by the time I'd finished, I thought, maybe there's some mileage in showing the rest of you. So let's dig into this one. This is the end product of the little cameo I've got here. So let me just fire that up. So I can hear you thinking that, well, it's just a police car with a flashing light. We've seen that plenty of times before, and it's very easy to use a PMP flasher kit to get that effect. But this one is slightly different. What we have here is the ability to determine how long the unit flashes for and the period of time that it's actually off. So for example, you could have that light flashing for say 30 seconds, then it'll be off for maybe up to 9-10 minutes, and then 30 seconds again. And the beauty of these small circuits is that you can dot them around your layout, especially a big layout, and because they will just keep on doing their own thing as long as there's power applied to them, it creates a lot of background interest. And this is the philosophy we've used for both of the WASAG exhibition layouts. We've got a bunch of very simple units dotted all around the layouts, and they just do their own thing right throughout the day. So this is a means of putting some units into your layout and just forgetting about them. So let's look at, whoops, if I can, wants to start doing its thing again. Right, the flasher. So the remit is very simple. We want a flasher unit of a variable duration. Now here's the interesting bit, no programming required. So it is programmable, but it's the hardware that will be doing the programming. The reason is that I know that many of the members are, let's say, the reluctant programmers at best. Some don't want to go near any programs. They're just not comfortable with software. And that's fine, because the simple way of doing this would be to have a short program in an Arduino or a custom PIC. But that's not for everyone. So what I want to look at here is to use existing circuits. Now, whereas folks might not be able to program, I would hope that everybody can build up a PMP circuit, because that's what we're going to use. We're going to use two PMP kits. The two kits, as you can see there, we have the versatile timer on the right-hand side, and we've got the dual flasher on the left. We will tie the output of the timer to the trigger input of the flasher. Of course, the timer is the programmable section of this, and it sets the duration of the flasher and also the period between the events. All looking good so far, except there's one problem. It doesn't work. So this perplexed me when I put these two together, knowing that the two circuits worked as individuals. But when I probed the voltage on the trigger of the dual flasher, I was not seeing 0 volts, and it needs 0 volts to trigger it. So at that point, I thought, well, I'll do what any other sensible person would do, and I'll give Davey a call. After all, they're his circuits. He looked at the two circuits, told me what the problem was, and gave me a solution. So let's take a look at the solution. So why does the thing not work? You have to look at the two circuits individually to understand that. And for all, I think all of the PMP circuits operate from 12-volt source, because the 12-volt source is the power supply that we're most likely to have on any model railway. But the versatile timer is a 5-volt circuit. The reason being that it has a PIC, and the PIC has to run off a 5-volt power supply. So what we have in that circuit is we have 12 volts going in, but there's a 5-volt regulator. which means that the output of the timer will switch between +5 and 0. Then if we take a look at the dual flasher, now that is a genuine 12-volt circuit. It's constructed using a 555 timer, which can operate from a supply of anything from about 4.5 volts up to about 14. So it's more than happy running directly from 12 volts. But this results in the trigger switching between 12 volts and 0. And perhaps those who've been on some of Davy's courses have already figured out the problem by now. There's a conflict between the 5 volts and the 12 volt circuits. What we need to do is to electrically isolate the two circuits, but couple the output and trigger connection. And the operative word is couple, because that's where we introduce the optocoupler. Very, very useful IC, which can be used in many different applications. And that's one of the reasons for bringing this presentation to this afternoon. So I'll refer you to Davy's online book, specifically chapter 18 on interfacing. And this diagram has been taken directly from that. Now, in the diagram, you'll see a small box shaded kind of a yellowish. And that is internally what you would see in an optocoupler. On the left-hand side of that, there is an LED, an infrared LED. And on the right, you'll see there's a phototransistor. Now, in practice, there are back-to-back LEDs so that this chip can handle AC circuits, AC signals rather. But simply when the LED fires up, so does the phototransistor. And therefore, what you see going in, you see coming out, but there is no electrical connection between them. So this is known as a level shifter. And the reason is that the input, which you can see on the left, goes from 0 to 5, which is the same as our timer circuit. On the right, the output goes from 0 to 12, which is what we need to operate the trigger of the flash unit. And also you'll notice it says non-inverting optocoupler. If you look at the waveform going in, it's also the waveform going out, but it is shifted by that voltage level. Occasionally you will need inverting optocouplers. So I'd again say refer back to Davy's chapter. This circuit has many possibilities. That's what it looks like in reality. As you can see, pretty small little 4-pin chip with a couple of dropping resistors. So let's go back to our original two circuits. Again, we've got the flasher on the left and the timer on the right. Well, let's join the two of them with the optocoupler. You might be able to work out here that what we have is that both circuits are powered by the same 12-volt supply. We have the output of the timer going to, the output of the timer going to the input of the optocoupler. The output of the optocoupler was actually soldered underneath the board, goes to the trigger. So okay, as far as the in and out's concerned. We then have, of course, 12 volts required on the output side. So this is directly fed from the 12 volt supply. And in the case of the input side, then we can take 5 volts from a 5 volt point on the timer board. So far, so good. Now let's see it in operation. There we go, so it works quite happily. In this case, I only needed to drive one LED, but this is a dual LED flasher. So in its full form, you could have two LEDs flashing, or in this particular case, I actually used a microlith LED. Had to be tiny to get underneath the inside of the blue light on the police car. But if you use the microlith LEDs, you could easily have two independent pairs of flashing LEDs. That would be ideal for a modern fire engine. And if you were to use that, put that together, then that would be the equivalent of quite an expensive one if you wish to buy it. As I said, it's a very simple, straightforward project. So are there any questions?